Good day, everyone, and welcome to this edition of the IPNSIG Academy. My name is Alberto Montilla, and I am a board member of the IPNSIG, and I'm glad to be your moderator today. Back in 1996, I started my professional career building mobile networks and bringing telephony to people and places that had never had it before. Since then, I've worked and witnessed the evolution from first generation to 5G, where we are today, and even beyond. An evolution that has achieved virtually 100% penetration of mobile services in our daily lives. With the increased space activity, many of us are wondering how we can provide the same level of communication and flexibility and simplicity that mobile networks offers today on the moon and beyond. Today's presentation, titled 3GPP, LTE 4G for Lunar Surface Communications, presented by Luiz Maestro from Nokia Bell Labs, will give us insights into the motivations and evolutions of mobile communications on the moon. Luiz Maestro is a principal engineer and a distinguished member of the technical staff at Nokia Bell Labs. He's also the principal investigator for the NASA Tipping Point program, aiming at deploying the first 4G LTE network on the lunar surface in late 2024. Luiz Maestro graduated in mobile communications from Miguel Hernández University in Spain. He started his career in Nokia in 2007 as an external radio researcher in Aalborg, Denmark. In 2009, Luiz became a member of the technical staff and later in 2011, head of Nokia's Innovation Center in Madrid, working closely with different customer innovation labs on the concepts and solutions for cellular networks. In 2013, Luiz moved to the US as head of Nokia Smart Labs America, focusing on smartphone and wireless network interactions and product innovation. In late 2014, he joined Nokia Technology and Innovation, later Nokia Bell Labs, and has been leading different innovation programs in the areas of ultra-compact, rapid deployable, and mission-critical wireless communications. Luiz, thank you for being with us today. Before we continue, I would like to highlight that Luiz will be taking questions at the end, so please post your questions in the Q&A sections of the webinar. With that, Luiz, the floor is yours.
Thank you, Alberto. Thank you for the kind introduction, and thank you for giving me the opportunity to speak to all of you today. Let me pull up my slides. Let me know when those are visible. All right. So as Alberto was introducing, I'm going to talk today about lunar surface communications, in particular 4G LTE. The agenda is more or less, I'll go through some introductory slides. I'll discuss why we believe that 3GPP communications will provide a benefit for lunar communications. I'll talk a little bit about how we see how we see the technology and the deployments evolving over time. I'll talk about our upcoming mission to the moon through the NASA Tipping Point program and with our partners from Intuitive Machines and Lunar Outpost. And then I'll discuss a little bit about high-level architectures and spectrum and regulatory aspects. So that's a little bit the outline for today's talk. For those of you who are not aware of it, Nokia Bell Labs is the research arm in Nokia. So basically, we try to research and do the hard things, and there is nothing harder than space. At least that's my strong belief, and that's why through the Nokia Bell Labs a powerful research machine, we are engaging in these activities. So a little bit of generic introduction. We all know that communications are critical for the future lunar economy. So no matter what lunar deployment we envision, whatever economic or industrial activities will necessitate advanced capabilities, be it voice, video, data, and control. So there's no other way around it. And instead of looking at proprietary technologies or proprietary solutions that are maybe developed once and reused for 30, 40 years, we believe that a standardized deployment, an architecture, and a service provider will benefit all the government, commercial, and private stakeholders of the future lunar economy. A little bit of background into some of the Nokia Bell Labs innovations that you may or may not know that have been actually revolving around space exploration and deployable communication. So going back even to the early 1960s, Bell Labs was providing some capabilities for some of the Mercury and Apollo programs. Bell Labs created, manufactured the Telstar-1 satellite, which was the first communication satellite to provide intercontinental TV broadcast. It was operated by NASA. Then if we fast forward to the mid 2000s, there was a lot of activities in terms of rapid deployable and critical communication research. So, for instance, Alcatel-Lucent developed and launched the 9907 rapid deployable network, which was a 4G WiMAX network in a box. At Nokia, we developed the ultra-compact LTE network, which was deployed in various form factors and scenarios, and provided a very compact LTE end-to-end critical communication system. We had activities with high-altitude balloon platforms like the Project Loon, providing coverage from the stratosphere. And more recently, we have we had two key activities that are basically taking us to space and in particular to the moon. In 2018, through our partnership with Vodafone, we engaged with a German startup with scientists in the Mission to the Moon program, which was about developing the first LTE network for live streaming HD video from the lunar surface. Due to circumstances beyond the control of Nokia, this mission never materialized. You all know how difficult missions to the space are, but that advanced helped us advance a lot of the technology, the concepts, and testing. And then in 2020, NASA awarded us with a tipping point program in order to develop an end-to-end LTE network for proximity communications in the lunar surface. And I'll talk a little bit about it in a couple of slides. So why 3GPP, why LTE and 5G for lunar surface communications? So I think Alberto was very nicely putting some words on that in the introduction. So 3GPP is a mature and proven technology. So there are billions of LTE subscribers globally. 5G is being heavily deployed as we speak. It's a technology that is continuously maintained and evolved in the standards with worldwide support from both the industrial and network equipment manufacturers, but also from the device side of things. The path to 5G and 6G is very well defined in the 3GPP standards. Many of the, if not all the devices that we can find in the market support multiple radio access technologies. So if you buy a 5G chipset, it is very likely that it also supports LTE and earlier releases, and the same thing that we see going on for 6G. These are all AP technologies, so that eases the integration possibilities with other technologies and applications. These are scalable in terms of bandwidth, data rates, number of users, power, deployment options. 3GPP, LTE, 5G are OFDM-based technologies, so these are very robust access technology that provides good protections against multipath and is very spectrum efficient. From the mobility standpoint, these technologies can support from static users, IoT devices, to high-speed mobility scenarios, like, for instance, a high-speed train with seamless data handovers across multiple sites. And last but not least, in terms of quality of service, the built-in dynamic quality of service or quality of experience framework enables, for instance, user and service and better differentiation. We have admission control and functionalities like that. So it makes these technologies very appealing. For instance, if you want to ensure that some mission critical voice traffic get prioritized over some background data downloads that are not mission critical. Some use case examples for 3GPP communications in space. Today, and in my talk, I'll be focusing mostly on the lunar surface communications. But if we try to think a little bit beyond, we have the moon. Why not Mars? Why not an asteroid? We can have lander to surface communications. Obviously, should EVA enabling EVA activities. We can also, through the same technologies, enable suit-to-suit communications. We can deploy or we can communicate with machines on the lunar surface. Those machines may be as simple as sensors that are basically science payloads, or machines that are doing in situ resource utilization. We can enable communications for rover when there is exploration activities on the lunar surface. And there are other use cases that we can entertain as well, like spacecraft to spacecraft communications for approach and docket maneuvers, EVA on orbiting gateways, and even, as you are probably familiar with, some space to surface communications are a possibility that the same technologies can enable. One thing that is critical for all of this to work properly is, let's not forget that we always need somebody on Earth that is monitoring and keeping an eye on the network. So I'll talk a little bit about the challenges of building an operations and maintenance solution for networks that are deployed in other celestial bodies. A little bit on the lunar surface communication evolution, how I see the path evolving. Obviously, this is not carved in stone. Time will tell, but I think in general we can see that we are going from custom products to hopefully commercial services. So what do I mean by that? So the first wave of activities are very mission specific, and that's, for instance, what I'll talk a little bit in a minute regarding the IM2 mission with the tipping point program. So it's a single mission with a custom built solution. This solution and design is very specific for a particular CONOPS, and sometimes you may have some proprietary solution. So you have little reuse across different missions. Then we move to multi-mission program type of activities. So we have common platforms and solutions. They are still deployed by each mission, but we are kind of standardized or highlighting or going one level up with respect to the CONOPS. So that platform can support multiple multiple activities with maybe perhaps slightly different CONOPS in those different missions. Then we move on to standardized solutions. So we have, established the standards. Those are used across the majority of programs and missions. We may be seeing a broader number of solution providers, and this is what we talk. When we talk about this, we think about we deploy these network once, and they may be reused across different programs. And then finally, we have the commercial service. You can think about it when we get to a stage in which there might be some more permanent settlement on the lunar surface. So we may deploy these networks once as semi-permanent or permanent infrastructure, and then the communication capabilities are offered as a service for the lunar economy. And this is standardized, so everybody that wishes to use the network can use a particular device, leveraging the standardized nature of the 3GPP technologies. And they can just tap into this mission critical communication network. So a little bit as the right hand side is what we see today on Earth. So when you pick up your phone, basically you are getting a commercial service from a particular carrier. It's behind doors. It's a standardized technology, and then basically you move on to a different service carrier, and you just change your SIM, and nowadays that's even easier with the eSIM concepts. So that's where we see the evolution going towards in the future. But let's take one step back. Let me talk a little bit about our tipping point mission. So as I mentioned earlier, in 2020, NASA selected us to build the first cellular network on the moon. So this is a 4G LTE communication system. We are working with two key partners for this activity: Intuitive Machines out of Houston, Texas, who are building the Nova Lander. And if you follow the news, you probably have seen their success in the IM-1 mission. So we are in the second mission of IM later this year. And then we have Lunar Outpost out of Colorado, who have developed the MAP rover. And that's a prospecting platform, basically. So our LTE 4G network will be integrated onto the Nova Lander and onto the rover, and it will provide the critical communications for the rover to transmit information back to the lander during the up to 12-day mission that will be carried out later this year. What's in stake or what it is that we want to do from the Nokia perspective? Well, obviously, we want to prove that we can deploy the technology in the moon. We want to verify the LTE 4G performance in broadly two main scenarios. One is short range, so within a few hundred meters from the lander, and then we will drive out with the rover and measure the system performance and the network performance at longer ranges. Obviously, the ultimate goal is to enable the TRL advancement of the technology so that we can pave the way for future missions and commercial opportunities. So how does this network that we are building for the tipping point program looks like? So it has multiple building blocks. So I'll start from the left-hand side. So we have LTE user equipment, or UE. So that's nothing more than a ruggedized, space-hardened LTE modem that will get integrated into the MAP rover. We also need custom-built antennas, and if I go back one slide, you'll see them here in the deployed configuration. Those antennas are are basically the UE antennas. So that's on the one hand side of the picture. And then what gets integrated into the lander is our LTE network in a box, which is basically more or less the size of a shoebox and contains two redundant end-to-end LTE networks. So what do we call NIP in this context for the tipping point? We're talking about the radio frequency boards, the baseband boards, the evolved packet core capabilities, and operations and maintenance solutions. We also have omnidirectional antennas on the lander. These are installed on the top deck of Nova C, and they will provide almost omnidirectional coverage around the lander. Why we chose omnidirectional antennas for this mission is basically to cater for the uncertainty in the landing, perhaps the different orientation and rotation of the lander upon touchdown, and to account for the uncertainty of the terrain, while we have simulated what the network performance will be on our target landing site. Things may be slightly different once we get there. So that's why we didn't want to go to a solution leveraging directional antennas and maybe complex mechanisms to steer those, but we wanted for this mission to err on the side of simplicity and robustness. Then we'll have a direct-to-earth link that is provided by our colleagues at Intuitive Machines from the Nova C lander, and then all the data will be received on the ground station that IM is providing. And finally, we'll have our own operations and maintenance solution, our own Nokia mission control center, if you will, that will enable us to monitor the system performance during the mission, and also, if needed, issue telecommands to modify some of the system parameters on the fly. So what are some of the challenges that we faced when building this LTE network to be deployed on the moon? So I guess none of this will surprise you, but it's definitely something that we spend a lot of effort and thinking into making sure that we build something that would properly operate on the lunar surface. So on the one hand side is environment, especially the survival of the launch during the Falcon 9 in the Falcon 9 rocket, but also the transit, landing, and operations on the moon in the vacuum of space. So we had to rebuild a completely different thermal mechanical design from our systems, so that they would operate in space, and harden many of the components that we were leveraging from some of our commercial off-the-shelf platforms, so that they can operate in space. Radiation. So unfortunately, on the moon, we are not very well protected against the galactic cosmic rays and protons from the sun. Even though this year is a solar maximum, so that's good in a way, because that will be a minimum for PCR. So I'm trying to be a little bit seeing the glass half full on this one. So we are mainly concerned for this mission, given the short duration on single event upsets, and then the multi-factor effect. So we did a lot of hardware modifications to our systems. We spend a lot of time implementing software robustness capabilities to cope and mitigate the radiation impact on our electronics. Size, weight, and power, as it's of utmost importance. So that's why we ended up building this super compact redundant system. We did a lot of software integration of different components into the computing platform. We replaced several components by lightweight hardware components, and many other optimizations in order to shave any ground that we could possibly shave from our systems. And as I was introducing before, in terms of remote control, operating the network from Earth, a network is deployed on the moon from Earth imposes some challenges that we often don't see when we try to operate a network on Earth. First and foremost, we can't send anybody to power cycle the system if something doesn't work well. So we have included a lot of self-healing and self-optimization capabilities in our system. We have built our own custom operations and maintenance solution that enables us to control the system, minimizing the use of the critical direct-to-earth link. So it's optimized for operation over low latency, low data rate links. So that's what we are doing for the tipping point. That's what we have been learning in this journey. That is basically coming to an end later this year. So how do we see future 3GPP enabled systems coming along? What are the key design principles? Obviously, that's our way to look at this. There might be some other possibilities, and other people may have different opinions and interpretations. But basically, our starting point is that any 3GPP lunar network that is built in order to meet the initial lunar deployments and mission requirements, its architecture should be expandable and scalable. So what we build today we should be able to leverage it and use it in future use cases and requirements. And that's not easy feat because of the challenges that I described in the earlier slides. You tend to then optimize for a particular mission or requirement, and then you need to find the balance so that this first key design principle is met. We have gone with the concept of network in a box. This lunar NIT is assumed to contain all the elements and network functions to provide a fully autonomous and independent coverage area on the lunar surface. And why is this important? Because the first wave of missions will not be evenly deployed on the lunar surface. So you may have one network being deployed in one place for a particular mission, another network deployed at a distance for another mission, and in the first wave of missions, you will not have all the capabilities to interconnect those networks. So it is best that each of the network nodes can operate independently, and as the network and capabilities expand in the future and inter-node communication becomes more robust and ubiquitous, then since you build something with modularity in itself, you can think about maybe disabling some of the capabilities in certain boxes while keeping other boxes at full capability. Interoperability is fundamental. It should be maintained across the surface 3GPP network, but also other integrated technologies and architectures following industry standards and blueprints, like, for instance, the LunarNet architecture. We still think that IP is the best baseline integration protocol. We can do, though, protocol encapsulation with other technologies like DTN or CSDS. This can be done, for instance, on host platforms where the 3GPP network components are integrated. So, for instance, think about a lander the lander can have these additional functionalities to do this protocol encapsulation. So we keep the 3GPP network standard, and then we leverage the economies of scale going forward. One thing that we believe it's fundamental, and we can see it from the network deployments on Earth, but also from our experience in doing the work for the moon. But coverage and data rates should be qualified with RF simulations, especially for the first missions which go to a particular landing area or location on the lunar surface. This is important not only to understand what the network capabilities would be, but also this information can be fed into the CONOPS planning of these missions. So, for instance, a rover somebody may decide to drive a rover over a particular area because they need to do something, but that area has poor RF coverage, so it might be best to go on a different route. So that's just one input that we can provide. And then finally, networking layers should be as much as possible transparent to the application layer, so we can have very nice integration of different applications and services on top of the 3GPP system architecture. So how that looks like in practice? Well, this is a very simplified block diagram architecture, but from the left-hand side, I'm looking at it from the principles that we are applying to the tipping point and evolving and expanding from there. So we have the antennas, we have the UE, we have the remote O&M agents, and we may have other RF surface communications that can be used as backup. Or you can think if you don't want to, if I don't want to be pointy about 3GPP may be backup. Well, we have other technologies on the surface that are primary. Especially if we think about some of the critical capabilities that are being deployed in future missions in the short term. Then host vehicles, you have your network in a box, you have your antennas, you have your O&M, other surface communication capabilities, but also you can have, or you will have basically direct-to-earth, the satellite relay, or LunaNet gateways integration point. And then basically the rest is what we get on Earth, ground station, and then mission control capabilities for operating the networks. Couple of words about the spectrum. If we look at the SFCG 32-2R5 recommendation, below 6 GHz, there are two key candidates for deploying a network on the moon. In the 2.5, 2.6 MHz range, well, we have usable bandwidth from N7, N38, and N41. Those cover both FDD and TDD technologies with different bandwidth associations. And then the second one is the 3.5, 3.8 GHz band, N48, 77, or 78. And these bands are pretty much TDD bands in what today constitutes the 3GPP spectrum policy. Other considerations, well, we would like to follow the SFCG recommendations as much as possible, including the coexistence with other spectrum users. However, we acknowledge that further analysis and discussions for future consideration, including alignment with national and international spectrum regulations, is guaranteed for the initial mission deployments. We looked a little bit about the PLM and ID assignations. Believe that the initial private network 999 MCC can be used for these first missions. And if we think about future network evolution with additional potential network service providers, well, those are that will necessitate further considerations, perhaps selections of other PLMN IDs for roaming purposes, for instance, but this is for future study. And I think this was my last slide. Looking at the time, I don't know if I went a little bit over my allocation, but I'll stop here and open the floor for questions.
Thanks, Luis. Fantastic. You know, I see the activity on the questions on the Q&A, and a couple of things that were really interesting to me. Luis, the first one is that my first job, I was that person who was pressing the reset button, going to the cell stations to, you know, put things in order. I agree with you that, you know, at least for a while, that won't be possible on the lunar surface, and having, you know, remote OEM is critical to that. So there are quite a few questions. I'm gonna go through the questions in order as they were written, and then I also have my own questions as well. So if for those on the audience, if you have questions, please, you know, again, go ahead and the Q&A, press the Q&A button and put your question there. So the first question is from Jorge Amodio. You in one of the slides, you talk about the, you know, the potential applications of 3GPP in different interfaces, and, you know, you show spacecraft to spacecraft communications. So the question is, in that scenario, spacecraft to spacecraft comms, how far can you go with 3GPP in terms of distances?
Yeah, so that's standardized. For instance, for LTE, I think you can get 100-kilometer cell radius without basically doing anything on the standard. So again, let's keep in mind that we want to keep things standards compliant. You know, you probably are aware of all the NTN, the non-terrestrial activities. So that's providing comms from LEO orbit mainly. So that's pushing the limit of the technology to way more distance. And I guess one of the nice things about spacecraft to spacecraft is that this space propagation. So if you have the antennas in the right place, you don't need to worry too much about you know, propagation losses. You need to be more concerned about you know, delays, especially for the RATCH procedure and synchronization and timing of the network. But that's something that, one, is standardized, and B, you can apply some proprietary solutions in order to extend the coverage of the network. So.
Awesome. Thank you, Luis. Then the next question is from Marshall Eubanks, and then this has more to do with concept of operations for that matter. So how does Nokia envision the black hole being on the moon? That is, suppose there are nodes on the far side, and the traffic has to get from the 3GPP network to a near side relay. Is it that 3GPP all the way, or does it transition to a high bandwidth point-to-point link?
It's a good question. So if we follow, for instance, some of the you know, goals that NASA has to deploy, you know, orbiting gateways around the moon, and other private companies that are basically planning to do that, and we look at the LunarNet architecture, I think you know, we should integrate with other technologies. I mean, if there is like this question, like you have something deployed on the far side, you want to basically communicate with the near side and then get all the way back to Earth, we need to leverage orbiting communication capabilities. You could do it with 3GPP communications all the way, but we are talking about a dense network deployment. That will not be the case in the next few years. So if I look you know, at the analogy of a cellular network on Earth, here you have a lot of deployments in which you basically have a cell tower. You may have a microwave link to communicate these cell towers across each other. You have a fiber or other technologies to connect these two nodes. You may be using also some relay functionalities, 3GPP relay functionalities, or integrated backhaul. But for a sparsely populated network, I think we need to use what other people are bringing, and that's why I mentioned the IP integration. It will help hopefully integrating with other technology providers, and then we need to close the gap with Earth. And I'm talking here about lunar surface communications, but let's think about Mars or beyond. So the interplanetary links are not 3GP based. At least I don't see that happen in any near future. So we do need to integrate with other technologies, and that would provide a very robust overall architecture.
Awesome. Thanks for the answer. Let's go to the next one. This is from Jose Carlos Garcia. And this is related, I think you answered the first part of the question. The second part has to do with the tipping point. In the tipping point demonstration, do you plan to keep the UE to the network in a box communication within the lunar surface only, or is any of this data coming to Earth?
The communication between the rover and the Nova Zealander will be basically surface. So the 3GP network will provide surface communications. However, through our ONM system, we are sending back to Earth all the telemetry that we can, all the KPIs, all the system information, and so forth. So the high bandwidth, low latency communication from the rover to the lander, or the lander to the rover, based on 3GPP, will stay on the moon. Then we have the direct to Earth link provided by intuitive machines, and that's what we will use to get all the data back to Earth. And with all the data, if I focus on what we are interested in Nokia, as I said, is like signal quality, data rates, modulation and encoding schemes used. So all the parameters of the system that will inform us, allow us to inform ourselves about the network performance at the different scenarios, and also use that information in order to calibrate our own RF propagation models. So basically, we think we know how the network is going to behave. We will know how the network has behaved. We compare the two. And then the next time that we do a simulation, it will be more accurate.
Awesome. And I'm going to interject one of my questions here because it is related to it, and it's related to the propagation model, all the way from, the first Okumura model to the COS 231 model. Do you envision that we are going to end up with a lunar specific model?
Well, we have in our team, we have one researcher that has developed a custom model for propagation on the moon. So it takes into consideration the lunar terrain profile. It takes into consideration the lunar curvature. It's different from terrestrial models. It shares some similarities, but we have calibrated that model actually in Fuerteventura, in one of the islands, in one of the Canary Islands, because the terrain characteristics were similar. And there are question marks still, like how is the regolith going to behave? How deep the regolith layer is, how charged the particles are, how transparent it is, and things like that. So I do think that we'll need to leverage these custom models, propagation models in the future.
Awesome, thank you. Let's go to the next question. This question is from Jacob Nielsen, and there are two questions on it. I think you answered the first one, which is which frequency bands will you be using for the LTE deployment locally on the moon, as well as the connection between the moon and Earth. You mentioned that they are basically following the recommendations so far. The second part of the question is what type of speeds are you expecting to achieve between the moon and Earth? And I would say probably in the two sections, right? First in the lunar surface for the demonstration, what type of throughput are you validating or expecting?
Mm-hmm. So for surface comms, our LTE system is capable of achieving 150 megabit per second in downlink. That would be from the lander to the rover, and then 50 megabit per second uplink from the rover to the lander. So that's it's a 20 megahertz single carrier system. So between Moon and Earth, then we are limited by the direct Earth link. And I don't want to talk a lot about it. This is our mission partners providing it. But you know that it depends on the which antenna are you receiving the signal or transmitting the signal from Earth. So it varies, but at least and obviously there are people that are developing technologies to have high bandwidth also on these direct to Earth links. But it will be, we can transmit 150 or the aggregated 200 megabit per second real time back to Earth. We can do that in this first mission, but future missions, I'm sure that there will be fatter pipes that we can use.
Yeah, and I imagine that as you make the deployment of networks in a box easier, you're always gonna have that problem, because it's not gonna be 100 meg down, 150 down. It would be probably 300, or multiplied by the number of cell stations or the number of systems that you have in the surface. It's a good problem to have, I would say.
Yes.
The next question is from Juan Friday, very interesting one. So far, you're targeting, with the demonstration, you're targeting a single user equipment to the LTV-G Node B in the Nova C rover. Is there a roadmap, or what is the roadmap regarding testing and validating shared access, basically having multiple UEs accessing the network?
Yeah, it's a good question. So actually, for the IM2 mission, we will have two users. The tipping point was focusing on the communication between the Nova C lander and the MAP rover. But actually, in discussing with Intuitive Machines, when we were ramping up the project, they had this concept that will also fly an IM2 called the Micro Nova C. So that's a mini version of their Nova C lander with its own propulsion system that will hop on the lunar surface. So they looked at what we were building for the tipping point, and they said, why don't we just get one of these UEs for our Micro Nova C hopper? It's called the vehicle, and we benefit from that as well. So that was kind of a slightly separate from the tipping point. That's why I didn't mention it from the get-go. But there will be two users on the Moon using LTE in IM2 mission. We have tested our system is capable of supporting hundreds of users. I mean, we have tested that on Earth. We are just not deploying as many users still on the Moon. But that's one of the things that it comes for free by using these 3GPP technologies. That it's basically multi-user capable from the beginning.
I think that's a great point, because if you look at that, for example, in CCSDS, and the challenge of how you make some of the proximity links now multi-access, this is something that even from the first generation of the cellular networks, it has been there, as you said, it comes for free. So talks about that. Next question is also from Juan. And it's a very interesting one. You mentioned keeping the standard unchanged is crucial from profiting from the economies of scale. How can this be achieved over backhaul links with latencies far beyond the one expected in terrestrial applications? Is 3GPP flexible enough to evolve and accommodate space use cases?
Yeah, so one answer to this question comes from the system architecture. So if you think about the concept of a network in a box, you have in that system an entire 3GPP network. And then what you integrate with is basically already your backhaul. So it's in a way IP packets. So what happens, and it's user data basically. What happens with that packet, we can think of even of integrating that with the bundle protocol of CCSDS and or whatever else. So that user packet, however, is sent back on from to or from Earth, that will not impact the 3GPP network performance. So by keeping all the critical components onto the same box, you are basically ensuring that you have a high degree of flexibility, even though you lose some flexibility by integrating everything into the same place. But that's what I was mentioning earlier as well, that as the deployments evolve, you can and the networks hopefully grow on the moon, you can select which NIPs will have certain functionalities. And maybe you don't have NIPs fully autonomous, or maybe you do, because it will depend very much on the CONOPS or the availability and reliability that you need to have in a certain portion of the moon deployment. So that's one way of looking at it. The other way of looking at it is that you look at the NTN standards. They are catering for longer distances from space to Earth. So the 3GPP standards are evolving in that way, but by architecting the system in the right way, you can actually alleviate and facilitate some of the complications that will come from the huge interplanetary distances.
Awesome. Thank you. So this is going to be the last question. Very interesting one, because it, I think, makes us think about the future. What is the plan for maintaining these deployments, the LTE deployments on the moon? I would imagine it refers to surviving the lunar night, how to power them, and anything that you would say would require any sort of maintenance.
Yeah, so it's a very good question indeed. I'll go back to one thing that I mentioned earlier, that we can do this in isolation. So, I mean, if communications is one piece of the puzzle, we need thermal, we need power, we need backhaul, we need many other things for this to be successful. So the initial missions are short-lived missions. So you rely on solar power, you rely on batteries, so that you can power up and keep your communication systems within the operational thermal limits. Going forward, lunar night survival is a key aspect, as you mentioned, but we need permanent infrastructure. We need permanent power. We need permanent capabilities to support the communication networks going forward, and we need to architect them in such a way that they are even more resilient and zero touch than the networks that we have on Earth. Going back to what we said earlier, it's unlikely that we will have a lot of people being able to push a button or do some maintenance. So even if you think about the first missions, hopefully in the Artemis program, the EVA time is precious. I mean, the astronauts go there to do science, and they are hours, and their schedule is full. So you can't expect them to be doing maintenance on a communication network. The communication network should be there to serve them, not the other way around. So that's why we put a lot of effort and emphasis on building smart networks that are capable of self-heal, with almost zero touch and no human in the loop. There are other aspects to consider when you deploy something long-term on the lunar surface. The radiation impacts, accumulation of dust, and so forth. I think those are technical engineering problems, not anything that is unsurmountable, but definitely something that you'll need to basically architect the networks and build them in such a way that they can survive a longer period of time with hopefully nobody doing anything about them.
Awesome, fantastic, Luis. Any parting comments before we go?
No, again, thank you so much for having me here. I know we had gone back and forth on my participation, but I'm really happy that we could make it happen today. So I really appreciate the opportunity, and I hope that the talk was good and that you all enjoyed it.
Thank you.
Keep an eye on the IM2 mission. So we are looking forward to it.
We definitely will, Luis, and thank you for being with us today and sharing this exciting vision and strategy towards enabling communications on the lunar surface. This is going to be as transformational as mobile networks have been on Earth. So with that, I want to thank everybody for joining today. If as you want to view or see other IPNSIG Academy keynotes, please go to ipnsig.org/events. If you have any questions, please reach out to our secretariat email address at ipnsig.org. Very important, IPNSIG is a nonprofit. Basically, we are all volunteers, and our mission is to expand interplanetary communications, but we have a cost associated to it. So please contribute to our mission to expand networking and through a donation. You can do that in the QR code. Go to the ipnsig.org/donate, or even using your mobile phone, texting 53555. And very important, please become a member of the IPNSIG. Share that IPNSIG is available for all of us to learn and then to contribute. We are more than 1,000 members distributed around the world. We can't wait to see the day we have our first space member. So that we hope that this happen within this decade. But please go ahead and share the news. We are available, free to join. And with that, I wanted to say thank you for joining today, and you will be redirected to a short survey. Please fill it out. Thank you very much.